Yeah. When he went to the UK, like on a talk show, like some people in the audience were shocked because they didn't know that Mrs. Brown was a dude. It's like, no, our old Irish ladies do not look like men naturally. No, don't be so racist. Oh dear. I didn't know you watched that. That's a very Irish show, and you like it.
Yeah, it's really nice.
So that's what you're going to bring back, the Irish culture you're going to bring back home. It's like, when do you see this show I found? It's, oh, yeah.
Makes sense now?
It makes sense now, yeah. Then, I was laughing at the biology teacher because he comes in, he says, oh, you know, because I didn't know about the different timetables. He says, oh, you know, the timetable's different this week. I'm like, what? Is it? I said, you got an email about it. I'm like, oh, did I? I didn't read it. It's like, you should read your email and your timetables or you'll miss your class. I'm like, yeah, no, it's okay. It's all right. It's fine. So then,
we won't judge you.
Yeah, then at 10:20, I hear a knock at the door going, is Mr. Collum okay? I'm like, why'd you say that? He's supposed to be in class. And he's not. So I went, who doesn't look at the timetable now? It was nice. I'll teach him. Judging me. Right. Now this last chapter is quite nice because some of it you do in chemistry, so it won't be that hard. And some of the vocabulary you already know. So it should be, I hope, the easiest chapter. I hope.
It's really easy.
Well, my dad is kind of like, I can't get
no, this is not China.
Yeah, you will get it here. I'm sure it's easy.
No, because it's a small part of it.
Also, it's in English, and things are easier in English than Chinese. Chinese is difficult, you see, so. Have we got a signal? We got light? We got light. Okay. Whoa. Nuclear decay. Starting the atoms chapter. Great. Okay, you got that? Why can't you go back to hard work and Faisal for the last chapter? Give it a try. Okay. So you might have heard of this before. Radioactive decay. Some people have heard of this before? Yes. Yes. True, it gives you superpowers, but for the most part it's bad. Yes. Yeah. Come on. What time is it? Oh, you're pushing it. Sit down. Who's with you? Oh, dude, come on. What happened to you? I know he had the shower because he was stinking up the place, but what was your reason? Huh? No reason? Does he smell nice? Oh, he ruined it. What's the point in showering if you're going to smoke, dude? Alright. So radioactive decay, also known as nuclear decay or radioactivity, these are all the synonyms for it, is the process by which a nucleus loses energy by releasing radiation. The types of radiation are alpha, beta, gamma. Now there's a lot here, and I'll explain it. But this is the definition of decay. The key thing here, if I can draw this, you have your atom, and energy comes off of it, just like that. And it can come off three different ways: alpha, beta, or gamma. These are the three ways the energy can be released from the atom. Do all atoms do this? No, of course not, because if they all did this, we'd have a big problem. We'd be exposed to energy all the time. No, only some atoms do this. What type of atoms? Unstable atoms. Unstable atoms do this. Okay, so if you can write this down, please. The alpha, beta, and gamma are the three different types of energy here.
What does the beta symbol look like?
B.
And then the gamma?
Like that.
Yeah, with the long thingy. And then, okay.
Got that? No, not yet. Got that?
Yep.
Yep. Go on. Yep. Okay. So, let's have a look now. Come on. There you go. So, an example is uranium-239. This is unstable, so we say it's radioactive. And this means it will decay. That is, alpha, beta, and gamma will be released from it. Have you ever heard of this element, uranium? Yep. Note that uranium-239 will not do this forever. Because, you know, it will run out of energy eventually. So it's a limited time. More about that in another class. So what are our three types? Alpha. So alpha is actually nothing more than just helium. Alpha is basically 2 protons and 2 neutrons. No electrons. That's all alpha is. Basically it's just a helium what you call it, isotope. Oh, I'm tired. What do you call it when it has a different charge? Isotope and...
Ion?
Ion, that's the one.
Good job, Stephen.
Yeah, I'm too tired. Okay. So what's the charge of alpha?
Positive.
Exactly what positive?
2 plus.
Plus 2. Plus 2 what?
Charge.
Ding! No, not what I was looking for. Plus 2e.
HE plus.
Plus 2e.
Oh.
Yeah?
No.
Yeah?
Yeah.
If you want to.
I do want to, in fact I do. Right, so, that's alpha. The symbol is alpha. Or this.
See, if we want to write the symbol, then we have to write -2 because it doesn't have electrons. Minus 2 is on the extra.
You mean up above the E?
Yeah. Plus 2.
Interesting, because in this lesson we don't actually care so much about the charge, so the charge is often left out from these symbols. But you're right, if you want to put in minus 2, go ahead. Plus 2. Aha, very good. Continuing. So beta. Well, I wonder if anyone actually knows. I didn't ask if anyone knew about alpha. Does anyone know beta? Particle? Very good, Lee. A beta is just a high-speed electron. That's all. And its symbol is beta. Or, does anyone know the other symbol for it?
E minus.
Yeah, no. Where's the minus? Where's the E?
E minus.
Top or bottom? Top?
Top.
No, bottom. On the left.
What?
Yes.
Weird.
It is weird, but that's important. So it looks like you're saying it. Well, I will get to that later.
Oh yeah.
Yeah.
The one on top is on with the like mass.
Yeah.
Like the mass.
Continue.
Are we gonna have any tutorials?
At the end.
Or we can.
I'll see me. Yeah. Continue. Yeah. Does anyone know gamma?
It's a very,
It's a what?
it's like.
Yeah. It's an electromagnetic wave. Gamma rays are high energy electromagnetic waves, and the symbol is gamma.
That is not what you do.
Give me a break, would you? Give me a break.
I did my discovery, I didn't.
I think some of you have studied this before. Yes? No?
Yep.
Okay, continue. Continue for one. Newton's first law tells us that atoms should not just decay. What is Newton's first law?
Something that first stays at first, something in motion stays in motion. Unless
So-
an unsettled size forces applied on it.
Right. So if something is at rest and suddenly moves, like the alpha particle suddenly is released, that should not just happen naturally. Something should be causing it. Right? So they shouldn't just decay. It must be that there's a force pushing them out. So what is the force that pushes them out? Well, this force that pushes these alpha, beta, gammas out is called the weak nuclear force. It pushes them out. The weak nuclear force, get ready for this now, it's weak, right? It's repulsive, okay, and it acts in the nucleus, and it's a very short range. So this force, it pushes out, it's repulsive, it's weak, and by that we mean it's not strong. What I mean by weak is that most of the time it's not successful in pushing alpha, beta or gamma out, because most things are not falling apart, most atoms. So that's what we mean by it's weak. And it's a very short range. After 10 to the minus 18 meters, the force no longer applies from the nucleus. Now that's very small distance, 10 to the minus 18 meters. So it's like as soon as it leaves the atom, the force is gone. This isn't like gravity that acts over a great distance.
But it's still stronger than that.
Yes, but the price you pay is it exists in a very small part of space. So for its brief existence, it's stronger. Yes. It's the force responsible for decay. I didn't say it today, but I said it last week. This is one of the 4 forces of nature. Got that? Continue? Yeah. Now you might wonder if there is some counterbalancing force, and we'll talk about that later. So, onto some familiar notation from chemistry. Proton number, we use the letter Z. What do you use in chemistry? Z as well? Good. You don't need to write this down if it's the same as chemistry. So the proton number Z of an atom is what? Go on. Don't be stupid. Well, hey, it's the number of protons. And this defines what the atom is. And that's important, which again you probably know from chemistry. The number of protons tells you what you have. So 1 proton means you have a...
Helium. Hydrogen.
2 protons mean helium. 3 protons mean...
Sodium? Sodium?
Lithium, is it? Lithium, I think. 2 was enough to learn, the rest are not important. Anyway, so you know this from chemistry, that's good. For example, 1 proton makes hydrogen, 2 makes helium, and we can look this up in something called a periodic table. Again, you know this from chemistry.
What is a periodic table?
Yeah, dude.
Nice! Nice!
I see you studying hard.
No, that's the table with lots of letters in it.
What do you mean, a keyboard? Right, what is this one now? Nucleon number A.
The number of nucleons.
Neutrons. Yes, hang on. Well, what is a nucleon? Do you know?
Number of protons and neutrons.
Correct. Number of protons and neutrons.
Number of nucleons.
You're correct, yes. Of an atom is the number of protons and neutrons in the atom. Normally the number of protons and neutrons are the same, but not always. Mostly they are, but not always. You don't need to write this down because you have this from chemistry. Now, the atoms of a chemical element can exist in different types. These are called isotopes. They have the same number of protons, and usually electrons, but different number of neutrons. Different isotopes of the same elements have different masses. So here's a famous example. These are the 3 forms of hydrogen. So on the first one, it's 1 proton. That's it. That's hydrogen. The second one is 1 proton and 1 neutron. It's still hydrogen because it has 1 proton. And the last one is what? Yeah, and it's still hydrogen. So these are all called isotopes of hydrogen. And again, this is something you did in chemistry, isn't it? You did isotopes in chemistry. Did you know or learn the different names for the hydrogen isotopes?
I got them. Protium, deuterium, and tritium.
Yeah, but we're not... Like,
Well pronounced. Yes?
We're not meant to...
No.
We didn't do them in this course.
We did.
The different names of hydrogen isotopes. We didn't do them.
It was there, but you don't need to know that.
Hey. All cool, dudes. All cool. Right. Okay, so you did this in chemistry as well, which is good. The extra neutrons make the hydrogen heavier. So, alpha, beta, and gamma have different penetrating powers. Yes. Yes.
Well, forget this one.
So your hand is able to block alpha, but it cannot block beta. You would need something like some piece of aluminium to to block beta. Gamma cannot be blocked by your hand or aluminium. You would need a big piece of lead or concrete.
Huh?
Huh?
They're big, so it still penetrates.
Yeah, you would need like,
A 6 plus.
yeah, like, I don't know, like 10 centimeters or
Depends
something.
on what the gamma ray is coming from.
But then when they wear these lead suits,
The lead
Yeah,
suits,
it doesn't really protect everything, but
Yeah.
it weakens the force.
the lead suits would certainly protect against alpha and beta, which is kind of the ones that are most harmful to your health anyway. So, I mean, you can see here clearly the gamma being green in the right amounts can give you Hulk-like powers, obviously. That's why it's green. You never noticed that before? No, it makes sense though when you think about it. So the gamma one is yeah, don't do that. The gamma one is the one that is hardest to block. Alpha is actually extremely easy to block. Not only can you block it with your hand, you could actually block it with a piece of paper. Could block it. Not only that, but I think like 2 meters of air could block it. So it's extremely easy to block. Yeah, because it's a very fat particle. You can either draw or write this down here. It's the penetrating power of the different particles.
If the gamma rays penetrate the human body, how does it get trapped inside that man and change into a Hulk?
Rex Banner was a very smart man. I don't know how he did it, but he did it. The alpha one is the one that you gotta watch out for. That will make you really sick really quick.
Alpha man, I'm not sure if it's a great
so that doesn't penetrate you.
thing.
No, it doesn't. Yeah. However,
Your skin cells.
yeah. Well, if you
Can
have
cause cancer.
if you have a cut, or worse, if you drink or eat something that's contaminated with alpha, say goodbye to your stomach.
You know what it would be?
That's true.
You scream, oh.
Well, this is all true. This is all true. Let's look in more detail what this means. But I don't think I need to look in more detail because you know this from chemistry. The upper number, protons and neutrons, and the lower number, electrons. Don't make me slap you. Protons. Right. During radioactive decay, there are 4 quantities which are conserved. So, what are the 4? They are energy. You knew this already. The energy before the particle is released is equal to the energy after the particle is released. This is called conservation of energy. You knew this one already. What else is conserved, do you think?
Size.
I don't know. Give me a physics term. We're saying mass, what else?
Volume.
Volume? My goodness, guys. Think else. Think something else. I'll give you a clue. You have to think about the laws in physics that say conservation of blank.
Momentum.
Thank you. Not heat. Conservation of momentum. So momentum is conserved. And then think about Kirchhoff's junction law. Yes, very good. So we have energy, momentum, and charge. Momentum, charge, and there's one more. What do we think it might be? So I'll give you a little picture just to help focus your tired little minds. Steady.
Power.
No, not power, just processing the image of the graph paper is high res.
No, I meant
Yeah.
conservation of power.
Oh, alright. No, that would count as conservation of energy anyways. The fourth one, so what you have is you have the unstable atom, and then the particles come out, so the energy is conserved, the momentum is conserved, the charge is conserved. So for example, if this loses one positive charge, it means what came off had one positive charge. What else? Anything else you can think of that might be conserved? No?
Is it related to size?
Kind of. Yes. The last one is the nucleon number. So the number of protons and neutrons before separation equals the number of protons and neutrons after separation. You should note these four things. Dictionary? Which word? Which word? Which word? Four? Fine. What word is she looking up? I want to know. Tell me.
Nothing.
Okay, fine. Do you have these four? Continue. Continue.
Quantities.
Is it?
No.
I'll find out later. I have my ways. Right. Can we continue? Yes. So, since alpha is 2 protons and 2 neutrons, then the decaying material will see its number of protons decrease both by 2. So, for example, when the alpha particle leaves, the alpha particle is made of 2 protons and 2 neutrons, so that means what was left here now has 2 protons and 2 neutrons less. Obviously, if 4 people leave a room, then what's left in the room is 4 people less. Makes sense? Now, beta is 1 electron. Then the decaying material will see its number of electrons decrease by 1. Again, this is obvious, isn't it? An electron leaves, so you have 1 less electron. But madly, this is the strange thing now, 1 neutron will become 1 proton in the decaying material. This is kind of quite weird. When the electron leaves, on its exit, it changes one of the neutrons into a proton. How it does this? Oh, it does it. It's strange. Why would a neutron suddenly just become a proton after the electron has left? But it does. This is what happens when the electron leaves. I know it's weird, but it happens during beta decay. Gamma has no particles, so nothing changes in this regard, although some energy is lost from the decaying material. So gamma is just a wave, so there's nothing to remove. When a radioactive material decays, we can represent this decay in equation form, something that you would have seen in chemistry. So I'll write that down here. Oh, not yet. One day there'll be half-life 3, but just not yet. Okay, talk to Newt about it. You would have done equations in chemistry, balancing equations. So likewise in physics we have something similar for alpha, beta and gamma, and this is not loading. Now it's frozen. Let me open up a new writing pad. I don't think you have to write all of this down. I'm going to give you a brief summary of it now anyways. Where's my paint? Graphics? Yeah, it's cool like that.
What are we looking for?
My paint,
Why?
because the other one I have open is frozen.
Nice.
Okay.
Yeah.
So it's a for no graphics, then for
Oh, not colour paint. But I suppose I could use that temporarily. Oh no, it's back. Don't need
The
colour
other
paint.
one would go was on and then
It'll crash. Okay, so let's say we have something, I'll just call it X, and up the top we'll have the nucleon number, which is A, and down the bottom here is the Z, proton number. And let's say alpha is released. So what is alpha? It's 4,2 helium. So that means whatever you're left with should have 4 less nucleons, and how many less protons? 2 less protons. So now the equation is balanced, like in chemistry. If you have a beta, if you have a beta plus E0 minus 1, what happens on the top?
nothing.
Nothing, it's still A. There's no change. Because the top here is a 0.
Yeah, but the one nucleon.
Yeah, one proton becomes a neutron, but that doesn't change the total. So the top here is still A. Even if a proton becomes a neutron, if a neutron becomes a proton. So if a neutron becomes a proton, then this becomes Z plus 1. But again, that makes sense because this plus this should equal this. And this should equal this plus this. So it's all balanced. And lastly, if you have a gamma,
No change.
nothing changes. Gamma 0, 0. No change in the number of protons, neutrons, or electrons. Now we'll look at some examples of this, but this is just a basic idea. Have you done equations like this in chemistry?
No.
No?
In chemistry, no, we didn't do this.
Okay, continue. Close. Okay. Lozen. Too far. Right. 2 questions. A small amount of uranium-239, that is 0.01 nanograms, is undergoing radioactive decay. Represent this decay as a nuclear equation. What is the recoil velocity when an alpha particle is released? At the speed of that, what is the recoil velocity when a beta is released? Okay, so let's do this bit by bit. Let's start off with what we have. So here we have uranium-239, and out from it comes an alpha, comes a beta, and becomes a gamma out of it. I don't have my periodic table. Does anyone have it handy? How many protons are in uranium? Is it? I thought it was more like 104 hours there.
239?
120?
Is it the 239?
No. No. That's the mass. I want the protons.
Oh,
92. This becomes some new material plus some alphas. You know what? Let's just say it's one alpha that comes out and one beta, just to make it easy for us. So this will be plus 1 alpha. Oh my goodness. Plus 1 alpha plus a beta. Japers. Right. Plus a gamma. What number should I have here to keep it balanced? Should still be 92. 91. Good. And what should I have up here? Very good. Andrew, can you look up and see what element 91 is? Letter?
TA.
Awesome. Right, that's part 1. Part 2.
Even this guy is radioactive.
Yep. What is the velocity when the alpha is released at this speed? Okay, so what you have here, you have uranium 239 here. This is before. And then afterwards, you have some new material. It will fly to the left, and then the helium will fly to the right. So what rule could we use here to get the speeds afterwards?
M1, M2.
What's it called? Yeah.
Momentum.
Conservation momentum. So M1U1 plus M2U2 equals, now, I don't know, we'll call this speed here, well, this one we know it's 0.05 c, so we'll call this one here x, is what we're looking for. Equals M1x plus 0.05 c M2. Now, we have to do something about the masses. How many nucleons are here? 4. And so how many must be here? 235. So we could say that this is 235x plus 0.05 c 4. Now, it's not 4 kilograms and it's not 235 kilograms, but that doesn't matter because it's the same proportion, and since it's equal to 0, whatever is the missing constant, I can cancel it out. So it only matters that I get the proportions right. So I can have x equals, that's a c here, not an x.
What does the C resemble?
You know it, dude.
Speed up.
No.
Yes. X equals minus 0.05 times c times 4 over 235. Okay. So,
0.05?
oh, that was in the question. That's the speed of the alpha.
Negative
55.84 meters per second.
Change direction.
Yeah, the minus is going to the left.
This one's going
Okay, part 3 now. Are you sure that's right, Faisal? It looks awfully small. Did you put in the C? 3 to the 10 to the 8?
Yes.
You did?
I did.
Now that looks better, thank you.
I did 0.5.
Thank you, Puan. I knew I can count on you.
It's close, yeah.
What?
This one's wrong. Minus 2.5.
No, you're not saying Puan is wrong.
Minus 255. Yeah.
Yeah, I'm saying 2.5.
Not 255.
Oh, Puan. What's this tree in here? Oh no, that should be in there. Oh wait, now hang on, did you speed it like constant on the calculator, or
No.
you typed in what?
Yeah, this is right. Times 10 to the 8.
Oh, yeah. What number is that? Looks like I can't count on anyone nowadays. Minus 255.
Yeah.
K emphasis. Ah, no, it is close. Okay, can I look at part 3 now? Can I scroll down? Yes, guys?
Yeah.
Okay. So part 3, the only difference is with the beta particle. So again, you have your 238, and then afterwards your 238 moves to the left, and your beta moves to the right. So conservation momentum. M1U1 plus M2U2 equals M1V1 plus M2 0.5C. Now, this here is 238 nucleons. No, it was 23. Oh, thank you. 239. Now, how many nucleons are here? Yeah, but I know it's 0, so now I need to say, in terms of mass, how big is this of a nucleon compared to nucleon? No. Is this the same size as a proton or 2 protons?
No.
How big is an electron compared to a nucleon? Half the size? No. Did you not do this in chemistry? I did.
Yeah, the size of a neutron?
An electron is not the size of a neutron. That would be blanking huge. What's the size of an electron?
It's smaller than the others.
Well, that's, yes, thank you, Mr. Obvious, thank you.
The electron is 0.
What?
Zero.
No, its mass is not 0, and its mass of a...
The charge.
Oh, we don't know, just tell us.
It's about 1,000th the size of a proton or a neutron. But you recall that I gave you a lesson on masses of proton, neutron, and electron.
You did?
Yes.
When did you?
Didn't I?
No.
I'm sure I give... Yeah. Which is about 1,000 times smaller than the 10 to the 27 minus 27 of the proton and neutron. Yeah, go on. Where did it come up? It was in fields, was it? Yes, it was actually. Because I was asking you to do things like get the acceleration of things. Keep going. That is it. Massive electron, yes. Yes, all I have memories. So it's about 1,000. So if we want to keep the proportions the same, this will be 239x plus 1 over 1,000, 0.5c. Now if you want to be more exact, you can put in the actual masses if you want. But that's not the purpose of this question. It's just to get you a sense of how fast they're going. Yeah?
0.05 or 0.5?
No, 0.5, speed of light is the speed I tell you.
The last question was...
Well, yeah, an extra 0. So, x equals 0.0005c over 239. What's that, please? Thank you. What is it? Minus 627. Okay. Yep. Lastly, how much energy does the alpha have? How much energy does the beta have? I don't really need to do this. Maybe you can just tell me how to do it. What type of energy does the alpha have? As it's flying away really fast from the kinetic energy. And the formula for kinetic energy? mv squared. Do you know the mass? Well, you do. It's the mass of 4 nucleons, 2 protons and 2 neutrons. So we know this. Is this known?
Yeah.
Yeah, I give it to you. It's 0.05c. So you can know it here. On the calculator, I'll just hit this in. 0.05 times 10 times 3 times 10 to the power of 8, and the constants for mass of proton and neutron is on the calculator. So we have 2 protons, which is constant number 1, and then 2 neutrons, which is constant number 2. So when I put that in, a half mv squared, I get 7.53 times 10 to the minus 13 joules. What would be a better unit than using joules? Electron volts, correct. This is 4.7 mega electron volts. Now, let's go back and do the beta. So the only difference for the beta is its mass is constant number 3, and the speed is faster. So the energy of the beta works out to be much bigger. 64 giga electron volts. Big difference.
Can you go back to the question?
That one? Yeah. Got that? Yeah? It's okay? Yeah. Alright, next. What? Oh.
How did you get the 64?
I just repeated what I did, except I changed the mass to mass of an electron, which is constant number 3 on the calculator. And the V for the beta was 0.5C. So I just backspaced and changed it, that's
That
all.
was gamma.
No, not gamma, no.
So how would we find gamma? Like the energy?
We haven't done the formula yet for that one, because it's a way of, there's a special formula for that, which we'll do later in the chapter.
What's the amount of protons?
2 protons plus 2 neutrons. And I've given you the masses of those, they're on the calculator as well. Constant 1 and constant 2. Okay, continue. Right. How many alpha and beta particles are released when uranium-235 decays into lead?
So
Yes?
the one, this one,
Yes?
one
Oh. It's a different... Oh, you forgot the square. V squared.
is, oh,
Yeah. Okay. Continue. So you have uranium-235. Some alpha, some beta, and some gamma is released, and it turns into lead-207. The question is, how much alpha and beta has been released so that the uranium becomes lead after it decays? So the uranium will decay and become lead. How much alpha and beta was released? So we have to balance the equation here. So we start on the left. We have 1 uranium, 235, and I believe you said 92. That's what we said earlier for uranium. Now, this we know will become lead of 207 and 82. So straight away, how many protons am I missing? 10 I'm missing. And how many nucleons? Much more than that. What's that? 28. Is it? Yeah, 28. So how can we work out how many alphas and betas has happened? Well, what we do is we write down...
Subtract and divide.
Yeah, or I prefer to do it as a simultaneous.
Why?
Subtract and divide what?
Subtract the numbers and then divide them. You get
Give me an example.
235
Yeah.
minus 207, you
Yeah.
get 28.
Correct.
28 divided by 4, you get 7. That's 7.
7 alphas.
Yeah.
But you don't have only alphas. You also
Yeah,
have
and then the beta, nothing happens to the mass.
Yeah, so there's 7 alphas and 10 betas.
Yeah.
How did I get 10 betas? Because I lost 10 protons.
Yeah.
Yeah. Probably.
Huh?
Tell me this is not simpler than
Probably.
someone tell me.
Can you just watch, please? Yes?
Probably.
You think 4 betas. Now, let's see. The simultaneous will give us the right answer. Just watch. Humour me. Thank you. as I was saying, we'll have X we forgot about the 2. Oh, so it's what to read then. So let's work out what it is. So X of these, we don't know how many, plus Y of these, and we don't know how many. We'll call them Y. Right, so what should 235 equal if we keep this balanced? 207 plus, yes again? 4x plus 0y. And then 92 should equal 82 plus 2x
minus y.
So we can say 4x equals 235 minus 207. So x is 235 minus 207 divided by 4, which is 7, isn't it?
Mm-hmm.
Yes, that's x. Now we put that in to get the y. So 92 equals 82 plus 14 minus y. So what's that? 4, is it? So congrats me. No, positive 4. Y is 4. X is 7. So there were 7 alphas and 4 betas. Faisal, if you got the right answer, then you can hold your head up high, but hang it in shade.
I said 7.
But
Yeah.
that doesn't make sense.
But what about, you didn't get the Y.
Didn't say anything about the Y.
Sorry, what's my question? How many alphas and betas?
Didn't have time to calculate.
Indeed. Right, is this okay, or is
No.
it what? What? This is just simultaneous.
Minus y and 0y.
How is it minus y and 0y? 235 equals 207 plus 7x plus, sorry, I should have said that 7 was added in later. Right, 235 equals 207 plus 4x plus 0y.
Okay.
92 equals 82 plus 2x minus y. Have you balanced equations in chemistry?
Yeah.
Is it similar to this or not? I don't know.
Of course not.
I don't know. I don't study chemistry. I don't care for chemistry. Is it very different?
Yeah, we don't do those equations.
You don't do simultaneous? Too advanced?
No, it's just different things.
But does this make, is this okay?
Yeah.
Go on? Is it okay? Continue? Yeah? Okay. Well, that's good. If you like, there's lots of practice. What do you think this symbol is? N10. Look, 1 and no protons. 1 nucleon and no protons. Neutron. Okay? Try these for a couple of minutes and then we'll start the next lesson.